All right. Okay, so hello. Welcome back to this class. Before we start, are there any questions about the homework? Or is anything? Yes?
If we know the proof of something is sort of given somewhere else,
Yeah.
sort of verbatim, can we refer to it, or should we just?
Depends on the thing in particular. You can always ask on the millions. But I mean, it's a graduate course, so generally speaking, if it's something that's particular, something that sort of assumed as a background course, for example, you want to use the fundamental theorem of algebra or something. Right?
Well, what I was thinking in particular was like, what I was thinking in particular was like the proof, the actual question, like 2A from the second week's homework, which was the proof of the Zurich topology is actually topology.
I think you should summarize it somehow. I mean, you could just say, this is proved in Hertzer in chapter 2, section 1, but, and the main idea of that proof is, so that would be fine. But again, it's a grad course, so don't worry about every little detail, something that's already written down. Okay? All right, so, good, sir. Any other questions or comments? All right, so our goal today is to prove one single statement, which is one of the main motivating theorems in algebraic number 3. So it's the following. Suppose you have a Dedekind domain R, which what we call is an integral domain that is Noetherian, for which every non-zero prime ideal is maximal. And it's integrally closed in its field of fractions. Noetherian, there are many equivalent characterizations. The one that we ended up using last time was that every ideal is finitely generated. Today we're going to repeatedly, amazingly a large number of times, use the following equivalent definition of Noetherian. Every non-empty set of ideals has a maximal element. Every non-empty subset S of ideals, not necessarily prime, ideals, has a maximal element. Maximal with respect to inclusion. So that's the definition of Noetherian, or the characterization that we'll use today, repeatedly. So here's what's true. If you have a Dedekind domain, you can consider a set associated to it. Well, actually, before you get into that, you can consider ideals inside of R. And the theorem is that if you take any ideal I inside of R, then it can be written uniquely up to ordering and so on as a product of prime ideals. This is a unique representation as a product of primes. Where, in case you don't recall, multiplying an ideal means the following. If you have two ideals, say I and j, then I times j is I times j is the ideal generated by all products A times B, where A is in I and B is in j. So this is an ideal that's generated by products. It's not the set of products of something in I and something in j in general. It could easily fail to be that. For example, suppose I and j are both equal to the ideal generated by x and y inside of the polynomial ring in two variables over a field k. Then the element x squared plus xy plus y squared, let's assume k is characteristic 1 over 2. Actually, I don't think we need that, but I don't think we need that. So this element is in I times j. because each summand in this representation is a product of something in I times something in j. But this is irreducible, so it's not a product of some. It's certainly not a product of two things. Okay, so that's an example.
If you've got cube roots of unity.
Just to fix ideas. Wait, cube roots of unity. Yeah, so let's just fix this to be q. Okay, now are you happy? Because over q this is irreducible. And in general you could do a similar construction by taking just any irreducible polynomial in some number of variables, and then noting that each factor is a product of things in here. Hence, this whole sum is in the product ideal, but it's not in the set of products of something in I with something in j, which is in general not an ideal at all. Okay? So that's what the product of two ideals is, and here this is the product of a whole bunch of prime ideals. It's the product of prime ideals of R. So for any Dedekind domain, for example, the ring of integers of a number field, you do have a notion of unique factorization. Not of elements, but of ideals. Here's an example of kind of the motivation for wanting something like this. If you consider the number field q adjoins square root minus 6, then consider inside of that the ring of integers, which is z square root minus 6. Then you have a number in there, 6, which factors as 2 times 3, but it also factors as in another way, which we could just figure out by taking, so an arbitrary element here is a plus b root minus 6 times c plus d root minus 6. So it just multiplies out ac plus ad plus bc root minus 6 minus 6 times bd. So let's see if we can find a way to write 6.
I've never seen this with
Oh,
root
wait.
minus 5.
What?
I know this one root minus 5 like immediately.
Well, I'm not doing that exactly.
Okay.
I can.
Square root minus 6 times negative square root minus 6.
Yeah.
Yep, so that's what we'll get if we think of a way to do that. That's a good way to do it. So root minus 6, that's actually the one that I wrote in here, times minus root minus 6. So if you look, it's minus and then minus 6. So that's plus 6 again. So those are two different ways. And if you if you compute the general norm of an element, the product of an element times its conjugate, you'll see that you can't write 2 as a product of two things in some non-trivial way. Either thing will be a unit. And likewise, you can't break up 3, and you can't break up either of these. So you've written 6 in 2 completely different ways. And each one you can't sort of factor further. But if you instead work with ideals, what you have is that the ideal generated by 6, not to be confused with this notation, so for concreteness already, OK times, or 6 times OK, this you can write uniquely as a product of 2 primes. And those primes aren't principal, actually. Here are 2 primes that do it. The ideal generated by 2 and 2 plus root minus 6 squared times the ideal generated by 3 and 3 plus root minus 6 squared. What do they squared? That's crazy. That's the way it is.
You know, you've got
Yep, that's right.
plus there, it's
Sorry?
obviously generated with 2 and root minus 6 or 3 and root minus 6.
Yeah, you could certainly change it to be like that. Thanks, James. So these two ideals are primes. So we have as p1 to the 2 times p2 to the 2. And this is the unique way of writing the ideal generated by 6 as a product of primes. Okay, so somehow this is much better than what you get with elements. With elements, you can't write them uniquely as products of irreducibles, but when you use primes, you can. And so I should emphasize here that there's a multiplicity. Okay, and these aren't principal, but this is the best you can do. This is as close as you get. And fortunately, there's a group that we'll introduce called the class group of a number field, which measures exactly the difference between how good of unique factorization you can get here and here. I mean, with ideals, you always have unique factorization, but if the class group's trivial, then you get a notion of unique factorization already with elements. And very often it is trivial, but it's a nice measure of failure. Okay, so the goal for the rest of today, and this is actually a pretty hard proof, so we'll have to work pretty quickly, is to prove this statement. Just this, that's it. That's all we want to do. And what we're going to do in order to prove it is prove that there's basically a free abelian group associated to any Dedekind domain. So here's a definition. A fractional ideal I, meaning K equals frac of R, of a Dedekind domain R is, well, it's a subset of K that's an R module that's finitely generated. So is a finitely generated R module that's contained in K. So it's basically just a slight generalization of ideal. Every normal ideal, except for the zero ideal, so let me put that in, it's a non-zero, it's a finitely generated non-zero. So every normal old-fashioned ideal of R, except for the zero ideal, is a fractional ideal. And here we're just extending it a little bit. And there's a little trick that allows you to see exactly the extent to which you're extending the notion of ideal. So let's just prove a quick proposition just to get a feeling for the notion of fractional ideal. So let's write it pretty tersely. I, any fractional ideal, is equal to alpha times j, where j is just an old-fashioned integral ideal, and alpha is an element of k. So here, I is a fractional ideal. And you can always, there always exists an alpha and a j, with j an integral ideal. Integral ideal means ideal that is literally contained in R. It's an old-fashioned ideal. And alpha is an element of k. So you can always write a fractional ideal as an element of k times an integral ideal. The proof is easy. Here's what you do. So by definition, our fractional ideal I is finitely generated. Therefore, it's generated by a finite list of elements. These elements are elements of the fraction field, so they have denominators. So just take the product of all their denominators, and you get a number beta, so that beta times I, well, it's generated by things that are all integral. They're all actually in O sub k. So beta times I is contained in OK. But because I is an OK, sorry, I'm using OK when I should use R. Because I is an R module, beta times I is also an R module. It's also preserved by the action of R. So this is an ideal. So beta times I equals j is an ideal, the usual integral ideal. And therefore I, which is 1 over beta times j, is of that form. So I equals 1 over beta times j. And then you just take 1 over beta to be this alpha. It's in capital K. Okay, any questions about that? So a typical example of, say, a fractional ideal, here's one example. 1/3 times the unit ideal in the integers is a fractional ideal in the integers. So that's an example of a fractional ideal. You get every fractional ideal just by taking an integral ideal and multiplying it by some non-zero element of your fraction field, of your field. Okay? Cool. All right, so that's the definition of fractional ideal. Now, in order to prove this unique factorization into primes, we're going to prove something that at first seems like it maybe has nothing to do with it, but we'll spend most of our work proving this other statement, and then we'll get this as a fairly easy consequence. So, here's the statement, the theorem. And I don't think this is easy to prove, but the set of fractional ideals in a Dedekind domain R is an abelian group under ideal multiplication. Under ideal multiplication. Okay. And if you're a geometer, if you take your R here to be a certain subring of the field of rational functions on a curve over a finite field, then this is just the group of divisors on your curve. So it's a familiar thing if you're a geometer. But otherwise, it's just some abelian group, all the ideals, all the fractional ideals. Okay? So let's prove this. And again, I warn you, this isn't going to be that easy. We're going to have to use a couple of tricks, and it's sort of technical. Okay? So follow along, and stop me if you have a question. So here's how we're going to prove it. A few things are easy. Usually in number theory, when you want to prove something's a group, all the one axiom is trivial, and then the one that isn't trivial is really hard. Like with an elliptic curve, you can prove that the set of points have a group structure in a natural way, and every axiom is easy except the associative axiom. Whereas here, every axiom is going to be easy except the existence of inverses, and that one's going to be hard. Okay? So first, closure. If you have two fractional ideals, if you take their product, that's the ideal generated by products of all the generators. Each of these is finitely generated, so the result is finitely generated. Done. So this is a fractional ideal.
And because it's a domain, we don't get 0.
Exactly. So there's no worries about accidentally getting 0. It's closed. Excellent. Thank you. Second, if you multiply a fractional ideal by OK, you get back that fractional ideal. Because this I is an OK module, therefore I times OK is contained in I, but on the other hand, 1 is an OK. 1 is in, I'm calling R here, so 1 is an R. So we have this. So the R, the unit ideal, is in fact the unit of the group. Unit ideal is the one element of the purported group. The associative law is also easy. If you have ideals I, J, and K, not to be confused with the field K, then the fact that you have equality here, you have to think about it a little, but it basically just follows quickly from the definition of multiplying products and the fact you have associativity in any Dedekind domain. Yes?
Can you use your proposition for that? I mean,
For what?
Is that?
Oh, yeah. You probably want to, I mean, for this, you can always reduce these sorts of things. In fact, almost any question about the axioms to a question about an integral ideal, which makes it easier to think about, if you like. Because you could just say, you can reduce the case of integral ideal, and this is just a standard thing you do in a first course in algebra or ring theory. Okay, so certainly you can do that. Thanks. But I'm not going to go into detail here, because this isn't hard. The hard part, though, is the existence of inverses. Oh, also, that it's abelian is easy too. Ij equals Ji just follows trivially because field is clear, at least for us. So inverses, or a Dedekind domain is commutative. Okay, inverses, this is the part. So that's what we're going to spend most of our time on today. So now let's focus on the question of proving that any fractional ideal has an inverse. That is another fractional ideal, so the product of the two of them is R, our Dedekind domain, unit ideal. Okay? And I'll do this by proving it for prime ideals. So suppose P contained in R is a prime ideal. So fix that. Now our goal, to show there is an ideal I such that I times P is equal to the unit ideal, the whole ring. So that's our goal. We want to prove that. And here's the candidate. Candidate. There's a D. I'm not into politics, as you can tell. Okay, so let's just try I equal to the set of alpha in the fraction field K with the property that alpha multiplies P into R, into the ring. So this is at first just a set, but it's closed under addition. If alpha and beta both have this property, well then alpha plus beta times P is also an R. It's closed under multiplication. If alpha and beta both do this, and alpha times beta will do this. Let's see, so alpha times beta P. Wait, is that even true? That's not true, is it? And in fact, it doesn't need to be true. All I want to know is that ideals aren't closed under multiplication. That's ridiculous. So it's closed under addition and multiplication by an element of R. Okay? That's all you need to show. So if you have an element R in capital R and an element alpha in I, notice that R times alpha times P, well, we can do that as R times alpha times P, but alpha times P is contained in R, so this is contained in little r times capital R. And that's, since little r is in capital R, this is contained in capital R, in the unit ideal. So this I is it's closed under addition and it's closed under multiplication by R, so it's an R module. So our hope is that it's a fractional ideal with the property that I times P is equal to R. Okay? So let's try to prove that. And this will require some trickery, which I want to get in the right order, because it is actually a little tricky. Okay, so we're going to fix a non-zero element, B, in P. And we'll use it for various reasons. We're going to have to do a quick aside and prove a lemma using the Noetherian property of R. Otherwise, we won't be able to get much farther. So fix a B in P not equal to 0. And then, of course, you have that the ideal generated by B, this sort of useful element, is contained in P, just because B is an element of P. And now, what I'm going to do is I'm going to observe, and I'll prove this over there on the blackboard in a second, that B, this ideal, contains a product of prime ideals. And then I'll be able to prove that one of those prime ideals is equal to P, and we'll be able to use that to do some sort of clever stuff. So I'm going to prove first a general lemma. So just stop thinking about this for a moment. Now step back, and now here's a general lemma, which we're going to then plug into this argument. So lemma, if I is an ideal of R, then there are primes P sub I such that P1 times up through P sub S is contained in I. And actually, a nice way to say this, to kind of think about it a little more nicely, make a definition for ideals. Say I, quote, divides J if I contains J. And this is a very sensible thing, because if you consider, for example, the integers, z, then I'll show you one example. Consider the ideal generated by 6. It divides the ideal generated by 30, because the ideal generated by 6 contains the ideal generated by 30. If you're a multiple of 30, you're certainly a multiple of 6. So you have that contained it. So in general, if I ever say an ideal divides another, I just mean that ideal contains it. Just a generalization of the usual notion of divides. So here you can think about this lemma really efficiently as any ideal divides a product of primes. And we're going to use that here in a moment to say that this P and, moreover this B actually, divides a product of primes. And that will be extremely useful because, I mean, the main thing we're going to use repeatedly is the Noetherian condition, but also that every non-zero prime is maximal. So we'll be able to match up things and really gives you a lot of power. So let me prove this right here, that every ideal contains a product of primes. Now that's going to actually, I think that the only thing we're going to use is that R is Noetherian. So it's not going to be a really tricky proof, it's just an application of the Noetherian condition. So I will delete that example, leave this definition up, and now prove the lemma. So this is just the most straightforward application of Noetherian that you can think of. So what you do is consider the collection of all, collection S, and the set S, of all I that don't work. That don't, I'll just say don't work. By that I mean they don't satisfy the condition of the lemma. They don't contain a product of primes. They don't divide some product of primes. Non-empty product, well, anyways, just a product of primes. So we want to show that this set is the empty set, and that will prove there are no counterexamples to the statement. So let's take, using the Noetherian property of R, a maximal element of the set. So take I and S maximal, which means that if you look at any other element of S, it doesn't contain I. In other words, if I consider any other ideal at all, and it does contain I, then it will satisfy the condition of the lemma. So that's good. So we take an I that's maximal. Now, if I itself is prime, then we're done, because it's just, we're done. That's easy. So we can assume that I is not maximal, or not prime actually. Take I maximal in this set, but not maximal in the sense of an ideal. Without lot, or we may assume, it's trivial otherwise, we may assume that I is not prime. Which, just from the definition of a prime ideal, or a not prime ideal, means that there's a product of two numbers that are in I, neither of which is in I. So there is an A and B, an array of R, with A times B in I, but neither A nor B is in I. So A is not in I, and B is not in I. And that means that if you take A plus I, which is an ideal that's a little bigger than I, by that I mean the ideal generated by A plus I, and multiply that by the ideal generated by B plus I, just multiply this out, and you see that this is equal to the ideal generated by AB, or the product, well, yeah, it's the ideal, for principal ones, it is true that. So it's the ideal generated by AB plus A times I plus I times B plus I squared. And notice that each of these ideals in this sum is contained in I. The whole thing is contained in I. Now here's the funny thing. The ideal generated by A plus I, that's bigger than I. Therefore it's not in the set S. Therefore it satisfies the condition of the lemma. So A plus I, not in S. So it contains, this implies that A plus I contains a product of primes, P1 through Ps. Likewise, B plus I isn't in S, so it satisfies the condition of the lemma, since S is the set of all ideals that don't satisfy the lemma. Therefore, B plus I contains another product of primes, Q1 through QR. Now look, A plus I times B plus I, that contains Q1 dot dot PS times Q1 dot dot QR. So now just reading through this, you see that this product of primes is contained in here, because this one's contained in there, and that one's contained in there, and this is contained in I. But look, we've just found a product of primes that I divides, that's contained in I. Therefore, we've got a contradiction. There couldn't have been any I that's in S. So we conclude that S is the empty set, which completes the proof. So proof done.
Do we really need the Noetherian condition for this one?
Yes, I wouldn't have been able to do anything without it. The problem is, what did I do? I chose an ideal I in S that's maximal. In a non-Noetherian ring, you can find a collection of ideals with no maximal element.
But we can drop the other conditions of the dedicated one here.
I think so. We didn't use any of them, as far as I can tell. So I think it's a general statement. I tried for 1 second to construct a counterexample in a non-Noetherian ring, but I didn't completely convince myself that it works. So here's what I think might be a counterexample. Take the polynomial ring in infinitely many variables, and then take the ideal that's generated by x1 to the power 1, and x2 squared, and x3 cubed, and then x4 to the 4, and maybe that ideal does not contain a product of prime ideals. But I'm not sure, actually, because I thought about it for a second. Maybe I does not contain any product of prime ideals. Any finite product of prime ideals.
It is x1 itself.
That's a good. Well, that's a good. Maybe it just contains the ideal generated by x1, which is prime. Yeah, you're right. That doesn't work.
I mean, you could cancel that one out.
It works.
You start
Oh.
with x2.
No, it doesn't contain the ideal generated, which is.
I read that backwards. It doesn't contain the ideal generated by x1, does it? No, it does, because it's, yeah. What did I do? Let's see, let me do this. You're right, it of course contains the ideal generated by x1, which is prime. So,
You can start with x1 squared.
we dropped that one.
Yeah.
Yeah, maybe that was just, okay. Touche, and now, and now, let's see, what about this?
No, just x2 times
squared.
x2.
Wait, what?
The ideal x2
Oh, right. Yeah. Right, now I'm
it seems like this contains a lot.
Yeah. It's easy to contain a prime ideal, including not. The other sort of crazy idea is to take maybe some infinite product of copies of F2 and do something using axiometers. That's kind of probably a better idea. So this is an example where it does. Contains a lot of them. So would that work with a product of copies of F2? That might work. I'm just thinking of, take the infinite product, not sum, but product of F2s. So it's a ring, commutative ring. And it's uncountable, because it's all sequences of zeros and ones, so it's uncountable. And then inside of it, there's an ideal, which is the direct, infinite direct sum, which is all sequences of finite support. Because, I mean, if all the finitely many of them are zero, then when you multiply, that's preserved. So that's an ideal inside of here. Does it contain any? The thing is, I think the prime ideals in here, they have to be uncountable, because when you quotient out, you have to get F2, I think. So this I couldn't contain any. I don't think it could contain a product of finitely many prime ideals. I'm just making this up on the fly, so could be wrong, but
Why is,
It is
yeah,
close. It is
well,
close.
this is probably stupid, but like, these are 1 comma all zeros, that doesn't generate a.
no, because if you push it out by that, you get an infinite product of fields, which is not a domain. So that's not a prime ideal. The way you get a prime ideal is you could take like 0 in the first factor and then every possible sequence that starts with a 0. That would be a prime. That's an example of a prime ideal. It's actually a maximal ideal.
Right. You need an infinite number of ones. So.
Yeah, exactly. You'd have sequences that are, all the sequence, a lot of the elements of the ideal in here with 0 in the first entry and anything else, none of those could be possibly contained in I, since I is tiny in comparison to them. So, Robert, did you have a comment?
I think the whole ring's countable.
Wait, no, it can't be countable because it's an infinite product, so its elements are all binary sequences, which is clearly uncountable because it's in bijection with the real numbers.
It's not the sum.
It's very big, yeah. If I put some, then that would be different, and then it would be countable.
That seems good.
Okay, cool. So I'm not claiming this is definitely right, because I just came up with it right now, so it could be wrong, but it should be an example. And this ring isn't very easy. So you can easily make some really bad ideals. Okay, so now back to our story. We now have this really powerful fact. Every ideal divides a product of primes in a Dedekind domain, in fact in a Noetherian ring. But, so let's see if we can combine that somehow with being a Dedekind domain to get something neat. So this ideal B divides a product of prime ideals, P1 through PS. Okay? And now, what can we get from that? So I'm going to look at my notes to make sure I don't mess up the argument. So yeah, actually, I am messing up here. This is a. There are a few preliminary remarks that I make in here before doing this. So let's just put this on the back burner again for a moment. So what's the situation? We have a prime ideal P. So this is prime. And I defined some R module I right there. And now, first thing I should do is just verify that it's actually a fractional ideal. Okay? So the argument is the following. We have our B, which is a non-zero element of P. Notice that if you multiply B times I, then, I is defined to be something where any time you multiply something in I times something in P, for example the B, you get something in OK, you get something in R. So this is already contained in I. So this has to be, this product is an integral ideal. So it's 1 over B times some, so I is 1 over B times some integral ideal. So I is definitely a fractional ideal. This implies that I is a fractional ideal. So that's the first useful observation. Another observation is that P is a subset of I times P, which, as I just remarked, is an R. So let's just think about each of these inclusions. Is 1 an element of I? Yes or no? The answer is yes, because 1 multiplies P into R, because P is an integral ideal. Okay? Therefore, P is certainly contained in I times P, because you're multiplying by 1 and maybe a lot of other things. So this inclusion is good. This is, right here, this is because 1 is in I. It's from the definition of I. Okay, the next inclusion, that's just because if you multiply anything in I times something in P, you get into R. So that's just from the definition of I. So you have this. So in fact, this is an integral ideal. And now we get to use a Dedekind domain, that we're working with a Dedekind domain. So we have a prime ideal of a Dedekind domain that's non-zero. Remember, every non-zero prime ideal is maximal. So the only possibility now is either P is equal to I times P, or I times P is equal to R. If I times P equals R, we're done. In fact, that's what will really be true. Okay? So either we have equality here, oops, we have it here, or we have equality here. Because every prime ideal is maximal. Every non-zero prime ideal is maximal. So if we had it here, we'd be done. So let's assume that we have equality here and deduce a contradiction. And then we will have proved the hard part and kind of all the other stuff. Well, it's a little hard, but this is the main gist of the argument, which I definitely want to get through since I only have 10 minutes left. So if we're in a weird case where P is actually I times P, we will deduce a contradiction. So today, unfortunately, this is, I think, what I'll be able to finish. I'll have to pick up with the very last part of the argument next time. So we will deduce a contradiction. So we have P equals I times P.
So, I don't know.
Yep.
Why is it B times I and R again?
So Y is
third line from
Here?
the top.
Here?
Yeah. B
okay. So B was chosen to be an element of P by definition. So B is in P. So I has a property that anytime you multiply something in I times anything in P, you always end up in R. Therefore it's contained. Okay, so let's start here. Okay, so we have this I, we know it's a fractional ideal, and we're under the weird hypothesis that P is equal to I times P. And now we want to deduce a contradiction. So why can't this happen? Okay, and now we're going to use this P again, and this lemma that I proved just a moment ago. So what we have is, we have this, but we also have that we have a product P1 through PS contained in this ideal B, which is contained in P is equal to I times P. So that's the situation we're in. And now what are we going to do? So what I'm going to do is I'm going to try to use this information to construct an element that can't possibly exist, and hence deduce a contradiction. And I will succeed at doing that. So imagine all possible products of primes that are contained in B. Let's just choose this one to have a minimal number of different primes. Just because, I mean, why not? It's just a, I'm not saying anything about uniqueness or anything, just take the one with the minimal S. So assume S is minimal amongst all ways of doing this. You can always throw in a bunch more, so just take it minimal. Assume S minimal. Okay. So if no PI were contained in P, you could deduce a contradiction as follows. If no PI contained in P, then for each I, we choose some AI in PI, choose AI in PI, and then you get that the product of the AI is then the product of the PI, which is contained in P, but P is a prime ideal, so you can have a product of things where, AI in P, AI not in P, AI in PI, but AI not in P. So there's no possible way that no PI is contained in P. In other words, if every single one of these failed to be contained in P, then for each one you could find some element that sort of witnesses it failing to be contained in P. Take the product of all those. That product is clearly contained in P, but it's a product of things not in P, and that's a contradiction to P being prime. So at least one of the PIs is actually contained in P. So let's just say P1. So P1 is contained in P. Okay? Without loss of generality. Also, we chose this to be minimal. So if we consider the product P2 out through PS, it's not contained in the ideal generated by P. And P2, and then you kind of just follow your nose. This cannot possibly, by minimality, be contained in the ideal generated by B. By minimality. So there's some particular element, D, that is in here, but not in there. And that's the element we'll show can't possibly exist. So there is a D that's in the product P2 up through PS. The D is not in the ideal generated by B, just by minimality. We're just using minimality. And now let's use that D. So P times that D is contained in B. Because
You're on
well, no, yeah, but see, the thing is, because we're in a Dedekind domain, P1 equals P, so I should remember. P1 equals P, because every non-zero prime ideal is maximal, and P1 is contained in P, therefore P1 equals P. So this P1, if I, so the product P2 through PS times P1 is certainly contained in the ideal generated by B. So if I put P1 here, as James said, then that product is certainly contained in B, but this is by the fact we're in a Dedekind domain equal to the ideal generated by P, the ideal P times the ideal generated by T. So we have this. And now we're in pretty good shape. So now look, see this D that we have? Well, if you just rewrite this, it says that P times, and this is really clean and neat, D over B, this is contained in R. So look, we just constructed an element of I. The definition of I was any element at all with the property that when you multiply it by P, you get an R. So D over B is in I. That implies D over B is in I. Because that's just the definition of I. If you look at the definition right here. And now, final thing, well, almost the final thing. So the next observation actually is, let's call this element C, is D over B. C, it's in I, but it's not in OK. Why is that? Oh, R. And it's in OK. And R, since, let's see, if it were, then D would be in the ideal generated by B. What is that? C is not in R because if C were in, if C were in R, that would mean that we have this divisibility. So if this were actually integral, then D would be in the so since otherwise you'd have that so D over B would be equal to some alpha that's in R, which would mean that D is equal to B times alpha, which would mean that D is in the ideal generated by B, which is exactly what we constructed the D to not be, right? So the C is definitely not in R. So we have an element that's in I that's not in R. Now, and the final cool thing is, so finally, and this is a new idea, this is the way this argument works. It's really cool. So notice that C times P is contained in P. So why is that? Why is that? So C times P is contained in
This PD is contained in B.
Oh, what?
PD is contained in B, right?
Yes, PD is contained in the ideal generated by B. Yes. So C is D over B. Yeah, it's just going to fall from that P, and then that's. Wait, it's just no. Oh. So why is C times P contained in P? P times, yeah, so it's contained, so you have this, so, because this is contained in
containing IP.
Okay, so let's see. So C times P. Yeah, you're right. That's it. C is an I. Thank you very much. C is an I. So CP is an IP, but IP is contained in.
Equal to P.
Oh, okay,
That's
good.
not right. That's just an R.
Five.
So that doesn't hold. Why is this contained in P? Once we get that, it's trivial. Now we wrote it down here. So
Everybody assume that?
Yeah, what was, isn't that
See,
just
see the last line of the,
Oh.
you know,
wait, of what?
That's
P equals IP?
No, that's what we're. Oh, right. Beautiful. Yes. We finally get to use our hypothesis. P equals IP. Very nice. Okay, thank you. Sorry about that. I forgot the hypothesis. Although, I mean, you can't prove it without the hypothesis. So this is it now. Let me just, since we're out of time, let me just explain the words of the very nice argument from here, which is we'll use a whole bunch of times. I mean, throughout the class. So the fact that CP is contained in P, the fact that CP is contained in P, well, just imagine taking a basis for P. P is a free Z module of finite rank. Take a basis for P, take the element C, if you write a matrix down for the element C, then you'll get an integer matrix. You'll get a matrix of integer entries. Therefore, its characteristic polynomial is monic with integer coefficients. That implies that C is integral. C is in Z bar. But that means that C is in R, which is a contradiction because, I mean, look right here, C isn't R. So we're done. So again, the very last step is just C preserves. C, there's a basis that you can write C with respect to so that it's a matrix with integer entries. Therefore, it's an algebraic integer. And that gives a contradiction.
If we're just working that into itself.
Oh yeah. So
You
what
can
if it's a
take
characteristic
this number
P?
if you want.
Yeah, that's true. Actually, maybe I don't know how to finish the argument in that case. So I'm not giving you the proof in that case. You can prove this in the case of characteristic P, but yeah, then you have to think about lattices in a slightly different sense. So there are lattices. So I'm not giving the conclusion of the argument in that situation. We can find it in Castle's problem in general. Okay, so I'm done, and I'll see you on Friday. And on Friday, I will apply this to showing that everything has inverse. Okay. Yes. What? Oh, yes. Neil Kolbitz is going to speak at 4:30 today, in exactly 1 hour, in the communications room B27. So it'll be right here. So if you want to go to the first crypto seminar, it'll be right here, back in this room, but in B027. And if you're new here, ask what it is, and it's the communications building is across the street and down in the basement. So this, I mean, the building is across the street. This room is down in the basement. Yes.
And then in the lemma,
Yeah.
so we require right back to your life, you know.
Certainly. Otherwise, there's no. I mean, it's just trivial. Yeah, because then you just take anyone to be zero.
Yes.
So yeah, they're all certainly non-zero. I didn't explicitly state that, but you're right. I think I know what I do, but maybe I forgot to know the word. It's fixed.
Yeah. I mean, I can do like 90% of them immediately, and then maybe a couple that. Yeah. I mean, even on the second one, I was more sides.
Another one.
To what degree, you know, do we have a converse to the
Yes, I
Dedekind
did.
implies
Do you wanna see another sign?
factorization? I mean, is there any kind of a key if you know that, then it's Dedekind, or
Yes, do
you
you
know
know?
something else?
I actually sent out emails to a couple of people. I didn't know your email.
There are various things. I mean, the optimal thing you would want
I
would
kind
be
of tried
that.
to just prove, like, you know, the parts of Dedekind, you know, it doesn't have to be in here, it doesn't have to be
If you
really
want me
close.
to
I
send
didn't really put a lot of work into it, but it seemed like,
I mean, you used every property of Dedekind domain to prove this,
yeah.
but there. I mean, you could certainly imagine all kinds of weird rings where I think you have unique factorization. Maybe where you just have. I don't know. Maybe not. Let's see.
So wait, if we have a unique factorization domain, that implies unique
I'm
factorization.
talking about indif primes. I'm only talking about
I know, no.
factorization primes. Yeah.
But if we have a unique
Yeah.
factorization of elements,
Yeah,
that
then it's
implies
easy.
unique factorization of
Yeah. Yeah.
ideals.
Yeah.
But didn't we say the other day that not all UFDs are Dedekind domains?
I think we did not conclude in any way. There are various claims going across the room. I don't want to make any claims.
I couldn't remember.
Yeah. No, wait. There was a trivial example. You take a polynomial ring with several variables. It's not a Dedekind domain because it has the wrong dimension, but you have unique factorization. So, yeah. So that's just a polynomial ring and a couple of variables as a counterexample. But maybe if you put the additional condition of dimension 1, then it's okay.
Coral dimension.
Yeah, call dimension 1. Yeah. Yeah, of course, assuming that it's a domain. Yeah. Yeah, so, yeah, I don't know what more general. I mean, I think usually if it's not, if you take like an order inside of a Dedekind domain, so something like Z adjoint 2I, then you should start asking about these. And I think for these, what happens actually? Well, I'll come back to that. I'm not sure exactly how to describe what happens, but this is a good example of something that's not quite a Dedekind domain. And where I think that it's not a Dedekind domain. Why? Because it's not integrate first. That's the problem.
Yeah.
Everything else. So I think that a little bit goes wrong with unique factorization at a certain, but it's almost okay. But I'll talk about
There's like
yeah.
a finite number of problems or something.
Exactly. Yeah. So
Other
the
than
index of this in the maximal order, which in this case is 4, or actually 2. It's 2. All right. See you later.